Okay, so this is the code. The top one is Euclid. The other one is the iterative GCD. And if you have some small numbers, they both run really fast, like GCD and Euclid. Okay, but if the number is really large, so let's say if I multiply this by 100, if you multiply both numbers by 100, then I know for sure that the GCD will be 100, right? Because 100 will divide both. And this will take like, let's see, it's still fast. So let's multiply by 1000. It's not that fast anymore, right? But 10,000, it's getting slow. Okay. Okay. If I multiply by let's see. Now I can keep walking. Okay. I can give you a snack and then you can go to the bathroom and come back and still this is still running. Okay. So really low, it's really slow. Okay, so let's see. So if I use Euclid, yeah, that's it.
Damn.
So let's multiply by 2 more 0, 2 more 0. Yes, really fast. Okay, so so you can it's really fast. Okay, the reason why it's really fast is because every time it works, it makes a recursive call. You divide the number by 2. Okay, so every time, not every time, at most 2 recursive calls, the number got divided by 2. If you think about this in terms of digits, dividing by 2 is like you don't decrease the number of digits, right? But if you divide it by 2 like 4 times, the number of digits in decimal decrease by 1. So how many times can you like divide? How many digits do we have? This is like 20 or maybe at most 30 digits, right? So you make at most like 100 divisions, which in machine is really like seconds, right? Less than a second. So that's the reason why it's run really fast. Okay. So dividing, the fact that you decrease the size of the problem by half, like really makes things different. Yeah. And this is also true when you want to compute power. So if you recall in RSA, how do we encrypt? We take the message and we raise it to some power, right? And how do we decrypt? We take the decrypted message and we raise it to some power, right? So if you want to compute the power of numbers, and if you keep multiplying, it will take forever. So let me show you the simple one. So if I want to raise x to the power of y modulo m, so I need a modulo thing because otherwise my numbers will get larger and larger and then it won't work. It's like the numbers will be like a million digits long and then it cannot, Python cannot handle it. Okay, so the simple loop for computing the power is like this. Oh, I forget to return. So let's say P1 so it takes quite some time. Maybe a lot. Oh yeah, quite some time. Okay, I would like to raise this to this power and then modulo with this. So take some time, okay? But if you recall, when we do the RSA this message will be like many, like 10 digits, and this will be 10 digits. But then the function power of Python return instantly, right? So math.pow is something else. Okay, good. Okay, so it's returned instantly. So how does this work? Okay, so how does this thing works? The idea is that instead of like keep multiplying this for this many times, okay, you try to do something a little bit clever. Okay, so the reason we need to learn this function was because we have already used it in RSA, right? But the trick, like dividing stuff by 2, like works everywhere, and it's like the key to efficient algorithms. So that's why I want you to see it once. Okay, I plan for you to actually do it by hands, but yeah, we won't have time for that now. Okay, so let's take a look at how this thing got implemented. Oh, and then we come back to see if Euclid is correct. Okay, the correctness of Euclid will be last. We'll come back to that later. Sorry. Okay, so how fast can we compute x to the y? This is a simple one, and it takes a lot of time. Okay, it's not that efficient, but this observation really help us. So this is called repeated squaring. So if you want to compute x to the 16, okay, you can multiply x for 16 times, or you can keep squaring. So x to the 16 is like x to the 8 square, but x to the 8 is x to the 4 to the 4 square, right? So if you keep squaring, to get x to the 16, you square the number for only 4 times. Only 4 times. So it's like dividing by 2, right? So if you square the numbers, then it's like the exponent decrease by a factor of 2. So you compute x to the y, it's like you compute x to the y over 2 square. Okay? And this actually works if the number of x, the exponent is the power of 2. So it's like x to the, compute x to the 128. So basically it's x square, right? So it's x and so on, right? So you actually square for 8 times, then you get x to the 128. Okay? How can we do that with the general numbers? Same idea works. So this is like the algorithm for when the exponent is the power of 2. So you basically compute, when you want to compute x to the y, you compute to the x to the y over 2, and then you square. So that's basically the algorithms. And how many times do you need to, how many recursive calls does this function need to make? It's log of y. Because basically, every time you make a recursive call, you divide the value of y by 2. So how many times can you divide a number by 2 until you get to 0 or 1? It's log of that number. So this, instead of like having to do the multiplication of y by y times, if y is 1,000,000, you need to multiply for 1,000,000 times, right? You only need to multiply for log of that. So 1,000,000 is like 20 times. So this is how things get really fast. If y is not a power of 2, you can actually do it. Okay, you basically round the number down, take the floor, and if y is an odd number, you just do the squaring. Otherwise, you if y is an odd number, when you floor down, you take the floor of y over 2, you lost 1. So suppose y is 7, you want to compute x to the 7. What you did is like you compute x to the 3, and then you square it, and then you multiply it by x. So that will be this case. When the number is odd, is even, you just compute the x to the floor of y over 2 and then you square it. Otherwise, you miss 1, right? So you need to multiply 1 here. Okay? So this is the function. So let me write it for you and see how it works. It works really fast. Okay? Okay, same thing. It's actually the same function. So basically, I can do this, and then I can even do the larger than this, right? Okay, like. Okay, it's run really fast. Let's add a few. Okay, so it's really fast. So the fact that the recursive call, you make only like log of the recursive calls, that's the running time, and the running time of log is like really fast. Alright, so now you know two things. You need the mod, okay? So if you ignore the mod, it won't work. So let me show you the version without the mod. Just ignore the mod. And let's try to run it with the smaller one. So let's try to do this with this first. Yeah, it's doesn't work anymore. Like Python doesn't like it. Let's do this. Yeah. So let's say set sys.set in oh. Okay. And then it's like take forever. If you don't mod, the number will be really large, and it eventually eats all my memories. So let me show you. Like, it might crash my machine. So 45x, 48. It's really slow. Keep taking my memories, or maybe it crash. Either way. I don't want to stop. Anyway, yeah, you take forever. Okay, just ignore it. Okay. All right. So you actually need a mod. Okay. All right. So at this point, you should know two things: TCD based on Euclid. Okay, and power. Both are recursive algorithms, and it runs in log of the number of the number of bits of the input. Okay. All right. So Euclid is run. It makes log x plus y calls, a recursive call. But when you actually do compute with these numbers, there will be another factor of log or log square on that, but we ignored it. Okay.